This lesson is about the relationship between the surface areas and volumes of similar solids. Similar solids have the same shape and proportional dimensions but different sizes. In other words, similar solids are like similar figures where matching heights or matching widths have the same ratio, except similar solids are talking about three-dimensional shapes. So for questions like number 1, when they ask, are these two shapes similar, that's a very familiar problem, just three-dimensional. You just match up the corresponding lengths and corresponding widths and corresponding heights and see whether or not the ratios simplify to be the same thing. So when you pair up corresponding sides and then you simplify them all, 6 and 8 both divide by 2, 18 and 24 both divide by 6. Yes, they do simplify to be the same ratio. So yes, they're similar, and the scale factor is either 3 to 4 or 4 to 3, depending on what order you chose to put it in. Pause here and try questions 2 and 3 on your own. Go ahead and check your answers. Notice how you need to check all the measurements that apply, including things like radius pairs, as well as heights. Now, here's going to be the key rule for solving the word problems you'll see today. If a scale factor of two similar solids is A to B, then the ratio of their corresponding areas, including surface areas, is A squared to B squared, and the ratio of their volumes is A cubed to B cubed. This actually should sound pretty familiar because you learned the first half of this, that for similar shapes, corresponding areas are the squared version of the ratio. You learned that at the tail end of chapter 10. It's just that now it has one more part. It's saying, well, not only does it apply to areas of flat shapes, but it applies to surface areas of three-dimensional shapes. And also, the volume ratio is going to be the same as the scale factor, but cubed. Let's use those rules to work through the first problem together. What is the scale factor of the similar rectangular prisms shown below? They're not telling you the sides of the shape, but they are telling you the volumes of each similar figure. So you can make a volume ratio. Because it's a volume ratio, you know it's a cubed version of the scale factor. So you could say A cubed over B cubed equals the ratio of the volumes. Now, a quick note. For me, my first instinct on a problem like this is to immediately cube root both sides to cancel out the cubes on the A and the B. But if I do that, I get crazy run-on answers for the cube root of 1728 and 3,375. So what you want to do instead is first simplify the fraction. So experiment with small prime numbers and see which ones will divide both numbers. 2 won't work because they're not both even. 5 won't work. Oh, 3 works. 3 works actually a great deal. If you're able to figure out that you could actually, right from the beginning, divide by the greatest common factor of 27, that's great. But if you just have to divide by 3 multiple times, that's fine. And you end up with the simplified version of the fraction, 64 over 125. Oh, that will actually cube root very well into a whole number ratio. So you have either 4 to 5, or if you put it in the other order, 5 to 4, for the scale factor of the sides of your two figures. We'll go through one more word problem together, and then you'll try the last one on your own. The volumes of two similar solids are 40 cubic inches and 135 cubic inches. If the surface area of the smaller solid is 48 square inches, what is the surface area of the larger solid? With these types of word problems, a good place to start is to figure out what sort of measurement, whether it's volume, surface area, or scale factor, you already have both pieces for. Right now we have only one surface area number, but we have two volume numbers. So what we have right from the beginning is the volume ratio. That's the only measurement that we have two of. So let's make our volume ratio. You could either say 40 over 135 or 135 over 40. It doesn't really matter. Now you want to simplify that fraction, and then you want to cube root it. Now you have the scale factor. So to recap, you figured out what type of ratio you had enough information for from the beginning, either the volume ratio, surface area, or scale factor. In this case, we knew 2 volumes, so we started with the volume ratio and used it to solve for scale factor. Now that you have the scale factor, look at the question. They're asking for the surface area of the larger solid. Since they're asking about surface area, we need the surface area ratio, and you get that by squaring the scale factor that you figured out. Now, you know one of the actual surface areas. You know that the smaller solid has a surface area of 48. Since that's the smaller shape, you'd line up that 48 with the 4, the smaller of the two numbers in your ratio. And we don't know the larger shape, so we'll put an x in that part of the ratio. Now you can cross multiply and solve. Don't forget your units, surface area, so inches squared. For number 6, a small box holds 18.5 ounces, OZ is abbreviation for ounces, that's a weight measurement, of cereal. The family size, or larger size box, is formed by scaling the dimensions of the small box by a factor of 1.15. How much cereal does the family size box hold? So first we need to figure out what sort of measurement we already have both pieces of the ratio for. We have an 18.5 ounce number. Ounces is weight, so you could say that's really volume. So they have one volume number and no other volume numbers. However, they do tell us that the dimensions or sides of the small box is increased by a factor of 1.15 to create the sides of the larger box. So in other words, we could say that they're telling us the scale factor is 1 to 1.15. So we already know the scale factor, so we don't have to do any work to solve for it. We already know it. Now we can look at the question, how much cereal does a family size box hold? That sounds like a volume question. How much cereal in ounces does a larger box hold? So pause here and see if you could solve the rest of the problem on your own. So they're asking about volume, so you need the volume ratio. That's a cubed version of the scale factor. Once you have your volume ratio, you can set up your proportion with the one actual volume you know. You know the smaller box holds 18.5, so you line up the 18.5 with the smaller number, the 1, and put x across from the bigger number. Cross multiply, and when you round to the nearest tenth, you get around 28.1 ounces for the volume of the larger box. Last question. So a small tip, and then you're going to try the rest on your own. An office supply store sells paper clips in small and large boxes. A small box holds about 220 paper clips. The large box is formed by doubling the dimensions of the small box. About how many paper clips should fit in the larger one? So here's your hint. When they're talking about the small box containing 220 paper clips, that's talking about how many paper clips fit inside of the space inside the box. In other words, paper clips are our units for volume. And last tip, when they talk about doubling dimensions, that means doubling the sides. So that's a fancy way of telling you scale factor. Good luck. Go ahead and check your answer. So you start off by knowing the scale factor. You could either use 1 over 2 or 2 over 1 to represent the doubling of dimensions between the smaller shape to the larger one. From there, you could calculate the volume ratio by cubing that ratio. Once you have your volume ratio, you could set that equal to a ratio of your actual full volume. So you know the smaller box has a volume of 220 paper clips, so that would line up with the smaller number, the 1, and you don't know the large one, so it'd be x. Cross multiply, and you get that the volume of the larger shape is 1,760 paper clips. Great job, everybody. Don't forget to turn in a picture of your notes on Schoology when you're done.